So we've been talking about the electric field created by a point charge. So here I have a point charge. I want to know the electric field right up here. This is a positive charge, so it makes electric field at this location away from it. That's easy. That's E1. Well, now I want a second charge, pretty close to it. That makes an electric field mostly up, but a little to the right. And then I'm going to do a third one. And it's mostly up, but a little to the left. And then a fourth one. And then a fifth one. And then lots more. And so as I add more and more here, we get more and more electric fields, and they're all different magnitudes because these are getting farther and farther apart. But if we always add the same number on either side, the x's always cancel, the y's always add up. So this leads us to the strategy we're going to use if instead of a bunch of point charges, we switch to a line of charge. So this is like, let's say, a plastic rod. We have charge sprinkled over the whole thing. I'm going to put an x and y coordinate system on top of it. So this is x, this is y. Here's our point of interest. This bar is length L, so I'm going to say it's centered on the y-axis. So this is x equals negative L over 2, and this equals positive L over 2. Here, if I wanted to calculate the electric field, I need to calculate each electric field and find its y component, and then add this one, and then add this one, and this one, and this one, and this one, and do it over and over and over and over and over. Well, that's what we're going to do here. But instead of doing a bunch of individual particles, we're going to talk just about one tiny piece of particle that is very, 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 very tiny. And it's so tiny, we're going to call it a tiny piece of Q, differential Q. Yes, we're pulling calculus into this. And it has a width on this bar of a little tiny piece of x. So dx has a charge dq. Now, the reason we do this is because when we add them up, if they are infinitely small, so instead of having 10 or 100 or 1,000, we can have an infinite number of infinitely small, so they add up to exactly this bar and exactly the total charge Q. So this whole thing has a total charge, I should have written that before, big Q. Then we get the electric fields pointing directly in the right direction. But when we add up a bunch of infinitesimal things, that's when it turns into an integral. So for us to calculate the electric field from this bar, we're going to integrate all these little tiny charges. So remember, integration means added up. So we're going to add together the electric field contribution from all these little charges. So this is the basic equation. In this particular problem, we really need to add up all the y components. So this turns into k ac dq, sorry about that, over r squared, times, if we do the angle from the horizontal, the y component is the sine of the angle. Now we need to make some substitutions, because as we're talking about this charge, we have one radius. Here, it's a different radius. Also, it's a different angle here than it is here. So if I define, or I just draw in, this is r, we know this is x because it's on the x-axis, and this point is y away. So I have my first substitution, r squared equals x squared plus y squared. Well, the angle, I need this component, or this piece of the electric field, this little piece of electric field, is at the same angle as the triangle, because it points directly away, though my picture is really bad. So the sine of this angle is opposite y over r, or y over r is the square root of x squared plus y squared. So I have put sine of theta in terms of y, which is a constant for this problem, and x, which is my variable. I've put r in terms of those same two things. So the last thing I have to deal with is dq. dq, remember, is the tiny little bit of charge. So that little bit of charge is to the whole charge, as that width, dx, is to the whole length. So this is a ratio. And we could go from here to solve for dq, but we're going to define a new quantity. Q over L, so total charge divided by total length, is going to be lambda. This is the first equation that you need to write down if you're, or box, if you're writing down everything. Lambda is the linear charge density. So density in chemistry was mass divided by volume, and you just called it density. Well, there are lots of different types of density. Density is a generalized term, actually, that refers to a ratio of two things. How closely or loosely is this thing packed or distributed? So this is charge over length. So linear length, charge density. Linear charge density, it's lambda. So if we rearrange this, dq equals q over L times dx. Q over L is this new lambda thing, lambda dx. So remember, this was our integral. Now we can actually set up the real integral. The electric field is equal to the integral of K, Coulomb's constant. It's a constant, it stays in the problem. Let me make sure everything's on the screen. dq, we just came up with, is lambda times dx. R squared is x squared plus y squared. Sine theta is y over the square root of x squared plus y squared. Now, some of you have asked me repeatedly for, why do I have to write that dx thing or that dt thing on the integral? And it's because we know what we're integrating with respect to. Here, we were adding up all the charges. Now we've made a substitution. Now we're adding up about across the length. And we need to, or we'll slide this back down, we need to go from where x is equal to negative L over 2, the left side of the bar, all the way over here. Because at each location, we're getting an electric field. And so as we sweep across from the left to the right along the bar, we add together all the electric fields. And because we've included the sign of the angle substitution, we're adding together only the y components. So the limits of integration here are negative L over 2 to positive over L with respect to x. So one thing I want you to notice about this integral. First, it looks yucky. But there's a lot of stuff in here that's a constant. K is Coulomb's constant, so it comes out of the integral. Lambda, the linear charge density, is the charge per unit length of the bar. That's a constant. It comes out of the integral. Y is the distance from the bar up to the point of interest. That's a constant. Comes out of the integral. Then, what stays in the integral, all we have in the numerator is dx. In the denominator, we have x squared plus y squared implied to the first power times x squared plus y squared square root. Well, remember, square root is the same as the 1/2 power. So I can put these two terms together. This is x squared plus y squared to the 3/2 power. Now, this isn't awful, but even those of you who are in calculus, you have not done trig substitution integration yet. So I'm going to make a second video to actually show the details between here and the next step. But this turns into, through the magic of calculus, 2k lambda over y, 1/2 L over the square root of 1/2 L squared plus y squared. So notice some features. We still have something like an x squared plus y squared term in here, but this is in the calculus video. So some of you were like, I don't care, just tell me what the answer is. Others of you really want to see the steps between here, and I will make that video. It will be posted shortly. So here is our answer. This is the electric field at this location from this bar of charge. However, I'm not going to box it, because This is not on the formula chart. It's kind of a pain to use. And it's important, but not hugely important. What we really want to look at is the two extremes. So I'm going to flip the page to copy this equation. E equals 2k lambda over y, 1/2 L over the square root of 1/2 L quantity squared plus y squared. And I want to look at two cases. First, what if y is a whole lot bigger than 1/2 of L? So much, much greater than. This is a mathematical term, so much greater than. So what is E if y is much, much greater than 1/2 L? So this is saying get really, 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 really far away from the bar. So to see that, we are going to first substitute back in. Remember that lambda is q over L. So I'm going to put q over L, y, 1/2 L square root 1/2 L squared plus y squared. So this L and this L cancel. This 2 and this 1/2 cancel. So we're left in the numerator with k and q. And this is a y. Well, in this term, we have a 1 over the square root of 1/2 L quantity squared plus y squared. So now we're going to apply this idea. If y is much, much greater than this, then, like if this is 1 and this is 1,000, then when you square 1,000 and then you take the square root of the whole thing, it's just going to be back at 1,000. So this is approximately equal to kq over y, 1 over, this is so tiny compared to this, that we can just write the square root of y squared. Well, of course, the square root of y squared is this y. So this is then kq over y times 1 over y, or kq over y squared. Look, it's the formula for a point charge, as it should be. If we flip back to the picture, if this is, you know, a ruler length, so 30 centimeters, but you're a kilometer away, you're not going to notice it's a ruler. You're just going to see it as a point. So if you're really, really far away, it makes sense that we get our point charge number back. The other case I want to look at, what is E if y is much, much less than 1/2 of L? So this means you're getting really, really, really close to the line. So in this case, again, I'm going to start from the basic equation that we derived, or from the other video is where I actually derive it. 2k lambda over y, 1/2 L, square root of 1/2 L squared plus y squared. So if y is much, much smaller, then this denominator is dominated by this term. So this is approximately equal to 2k lambda over y, oh, not equals, times 1/2 L over the square root of 1/2 L squared. So 1/2 L squared square root is just 1/2 L, and this is 1/2 L. These cancel out. So this is your second boxed equation from the video, 2k lambda over y. This is the electric field from an infinite line. And this is part of the reason that we have to do this linear charge density. If you have an infinite line, you actually have an infinite amount of charge spread over its length. But how closely spaced is that charge? No, there's no such thing as an infinite line. Really what it is you have a very long line compared to how close you are to it. And I want you to picture this in your head. If this is the line of charge, linear charge density, numerically, this might be something like 3 microcoulombs per meter. Notice it's in units of charge per unit length. So if this is a positive charge, then yes, at the middle, it makes an electric field away from it. But over here, it makes an electric field away. And over here, it makes an electric field away. And it makes an electric field radially away from it. So what I can't draw here is out of the paper up and into the paper down. So really, these are like pointing out, these are like spokes on a wheel, pointing out at all of these points. And this, we need to make this even longer so that these make sense. When you get close to the ends, it starts curving. But if you're far from the ends, the electric field is straight out, and it only depends on the distance away from the line. So that's part one of this video. We are now going to do an infinite plane. So 1, 2, 3, let me not lose my sheets. So our real goal on the first half of this was to figure out the electric field from a really long line at points far from the ends. Now I want to figure out the electric field near a really big sheet of charge. So for symmetry purposes, the way we usually start with this is, and I'm going to try to draw 3D, deal with it. So this is going to be a ring of charge along the X. Oh, wait a minute. No, this is Y. Sorry. This is Z. This is the X-axis. And I want to know the electric field at this point over here. Now this whole thing is positive, and the way we're going to do it on the calculus video is actually take the idea of a line, turn it into a circle. So we have a circle of charge, and then a bigger circle, and then a bigger circle, and a bigger circle. So after you find the electric field from a ring of charge, we turn that ring into a disk by stretching its radius from 0 all the way out to this radius, which is R. But again, the feature I want you to see is for this little piece of charge here, we get an electric field like this. This little piece of charge here, we get an electric field like this. This one, you get out of the page. This one, you get into the page. All of these cancel out. Please see it as 3D. And overall, your electric field is only in the X direction. So again, go to the calculus video if you want to see the details. We will use here surface charge density, where sigma equals charge per unit area. So now we're going to spread the charge evenly out over the whole surface. So we have sigma. And so through the amazingness, it's not magic of calculus because it's not magic, it's science, but through calculus, we figure out that the electric field of a disk is 2 pi k sigma times 1 minus x over the square root of x squared plus r squared. So distance away, x, radius of the disk, big R, and then some constants. 2, pi shows up, probably not a surprise since it's a circle, Coulomb's constant, and then surface charge density. So, and this makes sense, the more surface charge density, the more charge, and so the stronger the electric field. And then we have this interesting distance dependence relationship. So what I want is a really big disk. So this disk is so big that R is much greater than X. It's so big that if you're standing at X, you can't even see the edges of the disk. So in order to do this, we're going to rewrite this term. And so since this is all constants, what I really only need to deal with is this term. So if I have 1 minus x over, and I'm going to rearrange this one, and I'm going to turn it into 1 minus r squared over x squared times x squared. I've factored out an x squared. And always when I factor, I feel a little concerned, so I always double check by distributing. X squared times 1 is x squared times r squared over x squared, the x squared cancel. Ooh, except that should be a plus sign. Wow, shame on me on my short sheet over there. So what I can do now, 1 minus x over, I'm stuck with this term that's kind of like the Pythagorean theorem, but I can separate. The square root of x squared is just x. It's outside the square root now. And notice, then the x cancels. So I have 1 minus 1 over the square root of 1 plus r squared over x squared. Well, now I'm going to apply my condition. R is much, much bigger than x. If r is much, much bigger than this number becomes huge. When you take the square root of a huge number, it's still a big number. But when you do 1 divided by a big number, this whole term goes to 0. So this is, if for a really, really big disk, this whole term inside the parentheses of our electric field is 1. So we get the electric field is 2 pi k sigma. Box. Oh, I should have boxed surface charge density. Sorry about that. So this is for an infinite plane. If you are so close to a large sheet of charge, or if it really is an infinite sheet of charge, it's a huge sheet of charge, if you can't see the edges, then the electric field is given by this expression. Now, notice something about this expression. There's no x. 2's a constant, pi's a constant, Coulomb's constant, and surface charge density. That's just how much charge is there. So this is saying that no matter what distance you go from an infinite plane, you're always going to have the same amount of electric field. So one way of seeing that, if I can try to draw an infinite plane, pretend this is infinite, but if you're really close to it, your biggest contribution of charge is going to be the closest stuff, because the farthest away, it's so far away, it's a really small contribution to the electric field. Well, as you're farther away, these actually are a little weaker on you, so you start seeing more of it. It's almost like tunnel vision, like a cone, that you see just a little bit, and then you see more, and then you see more, and then you see more. So these effects just happen to cancel out exactly. And again, for the real proof of where this equation comes from, go look at the calculus video. But this approximation is quite valid. As long as it's a big enough plane that you can't really see the edges of it, the electric field is the same at all distances away. So I want to do one summary page just to wrap this up. If we have a point, the electric field is kq over distance squared. If we have an infinite line, the electric field is 2k lambda over the distance. And I have switched to r here just to match up with this. Y over there was distance from the line, r over here is distance to the line. And remember, lambda is linear charge density, charge per unit length. For an infinite plane, the electric field is 2 pi k sigma, no distance dependence, and sigma is charge over area. So this is your summary for this next assignment, where you'll be mostly working from the first assignment. The in-class one is infinite line, and then the homework one is infinite plane. So stay tuned for the calculus video.